What if software could not only write itself, but also orchestrate entire complex projects autonomously, moving far beyond what we traditionally think of as coding?
Right.
This isn't science fiction anymore. It's really the dawn of agentic AI systems. We've gone through a stack of truly insightful sources on this monumental shift in software engineering. And our mission today is, well, to cut through the jargon, extract the most important nuggets, and give you a clear understanding of what this new era means.
Yeah, what it means for the future of tech, and importantly, your role within it.
Exactly.
And, this deep dive, it goes far beyond AI as just a simple coding assistant.
Right. It's much bigger than that.
It really is. We're talking about AI becoming first-class citizens in software development, systems designed to understand high-level goals, break them down
into actual steps.
Yeah, actionable steps, interact with tools, and critically learn from feedback. The aim here, and it's profound, is achieving previously unimaginable scale and complexity in software outcomes. So the developer's role, it's genuinely transforming from, say, a builder of applications
to more of an orchestrator.
Precisely. An orchestrator of intelligence. You're shifting from writing every line to designing and governing these AI-driven workflows.
That's a huge shift in perspective. So, okay, if these systems are going to achieve such incredible things, the obvious first question is, how do you even start? How do you architect something so intelligent, so autonomous?
Yeah, what kind of foundational choices are involved?
Right.
Well, it's really about rethinking the blueprint. The fundamental shift with agentic AI isn't just about, more automation. It's about shifting the very locus of control in software.
The locus of control. Okay.
We're moving from explicitly programming every single step to defining high-level goals and letting these autonomous agents, reason and adapt their way to solutions.
So they figure it out themselves to some extent.
To a large extent. And this demands a robust foundation. A primary architectural decision really revolves around microservices versus a well-structured monolith for these AI-powered applications.
Okay. And what's the prevailing wisdom there, especially with AI's, unique demands?
Microservices are overwhelmingly preferred, and for good reason.
Like what?
They offer independent scalability. That's critical because an AI and inference workload is vastly different from, say, a data ingestion task. You don't want them bottlenecking each other.
Right. Makes sense.
You also get fault isolation. If one AI component fails, it doesn't necessarily bring down the whole system.
Okay. Resilience.
Exactly. And importantly, they give you technology flexibility. Different teams or components can use the best tool, the best model, for their specific AI job.
Got it.
Now, that said, in practice, a well-structured monolith can be a pragmatic starting point, especially for smaller teams.
So it's not always microservices from day one?
Not necessarily. The key, though, is to build it with modularity in mind, so you can easily break it down into microservices later as things get more complex.
Okay, plan for the future decomposition. So microservices give you that crucial agility, that resilience, but you mentioned a specific pattern within that framework, the model as a service, MOS.
Ah, yes. MOS. It's a specific microservices implementation where each AI model could be an LLM, could be a specialized smaller model, is treated as its own dedicated API-driven service.
Okay, so each model gets its own little service.
Exactly. And this is incredibly powerful because it enables advanced MLOs practices, things that are essential for continuous improvement.
Like A/B testing models.
Precisely. A/B testing, different model versions in production, or canary deployments where you roll out a new model gradually.
Slowly introducing it.
Right. And crucially, it allows for hot swapping models in production without any application downtime.
Without downtime. That's huge.
It is. Imagine upgrading your core AI logic on the fly, and your users don't even notice.
That completely changes the game for iteration, doesn't it? So MOS isn't just about efficiency, it's really about agility, constant evolution.
That's the core idea.
But, okay, beyond the high-level architecture, the devil, and maybe the brilliance, is in the details, right? Our sources talk about several key design patterns that make these systems truly robust.
Indeed. These patterns are like the scaffolding. They help manage the inherent chaos, the unpredictability of AI systems.
Right. What are some key ones?
Okay, first, the orchestration and mediator pattern. This centralizes complex, multi-step AI pipeline logic.
Like that ARGI example you mentioned earlier.
Exactly like ARGI. You receive a query, generate an embedding, query the vector DB, get context, build a prompt, call the LLM, post-process. It's a lot of steps. The mediator pattern decouples these components. Each part doesn't need to know about all the others.
Yeah.
Makes the whole workflow much more flexible.
Okay. Central control, but loose coupling.
Precisely. Then we have the command pattern. This encapsulates inference tasks as objects.
Why do that?
Well, AI inference requests aren't simple function calls. They often need to run asynchronously, maybe get queued during high load, retried if the model API fails.
Or logged for auditing?
Yes, exactly. Wrapping the task in a command object lets you manage these real-world ML workloads reliably.
Makes sense. What else?
Next, the factory plus registry pattern. This gives you a dynamic, centralized way to manage multiple AI models and their versions.
So if you have different model providers or versions.
Right. This pattern allows for that hot swapping we talked about. You can switch models just by changing a config value, not deploying new code.
Yeah, connecting back to Moz. Very neat.
Yeah, they work well together. And finally, the chain of responsibility pattern. This creates flexible pipelines for pre- and post-processing data.
Like cleaning data?
Yeah, sanitizing PII, normalizing text, tokenizing. You can easily add, remove, or reorder these processing steps without touching the core code or the individual handlers.
So these patterns, they work together. It sounds like the factory manages the models, command handles the inference, mediator orchestrates, and chain of responsibility preps the data.
You got it. It's not just a random collection. It's really a blueprint for resilience when you're dealing with AI's specific challenges.
Okay, that paints a clearer picture of the internals. But with all these models, all these services flying around, how do you manage them all? How do you secure them? And crucially, how do you control the costs? Because these models aren't cheap.
That is a huge concern, and that's where the AI gateway comes in. Think of it as a purpose-built control plane, specifically for AI.
More than just a standard API gateway.
Oh, yeah, much more. For unified access and security, it centralizes authentication, authorization, API key management across all your models.
One place to manage access? Good.
Very good. For cost management and rate limiting, which is absolutely vital with per-token pricing.
Yeah, that can get out of hand fast.
Right. The gateway tracks usage, enforces budget caps. It literally saves you money. It's also key for centralized observability, logging every request, every response, capturing performance metrics. Debugging distributed AI systems is tough without this.
I can imagine.
And a sophisticated AI gateway can also do intelligent routing and load balancing, meaning it can send simpler, cheaper queries to smaller, faster models and complex ones to the more powerful, expensive models, optimizing for both cost and performance.
Clever, like a smart traffic director for AI requests.
Exactly. And finally, response caching. If you get the same query often, caching the response dramatically reduces latency and, again, those API costs.
Okay, the AI gateway sounds absolutely mission critical, like the central nervous system for the AI operations.
It really is becoming that.
Now, let's shift gears a bit. Let's talk about maybe the most mind-bending capability, AI writing code. For those of us who've spent years writing code manually, it still feels a bit like magic. How do LLMs actually do this under the hood?
Yeah, it can feel like magic.
Yeah.
But the mechanics are quite fascinating. At its core, an LLM predicts the most probable next token-think word or symbol in a sequence.
Let's super autocomplete?
Sort of, but way more sophisticated.
Right.
It involves tokenization, breaking the input into those logical units. Then, embeddings and positional encoding turn these tokens into numbers, into vectors that capture both meaning and position in the sequence.
So it knows what the code means and where it is.
Exactly. And the self-attention mechanism is key here. It lets the model weigh the importance of different input tokens. It figures out which parts of your request or the preceding code are most relevant for generating the next piece of code.
Ah, okay.
Most modern code-generating LLMs are decoder-only and autoregressive. They predict one token at a time, building the code piece by piece based on what came before.
Got it. Building it up sequentially.
Now, a really crucial implication of this process, and something Martin Fowler points out very clearly, is their non-deterministic nature.
Meaning they don't always give the same answer.
Exactly. Giving an LLM the same prompt 100 times, you may get 100 different outputs.
Wow.
And this isn't just a technical quirk, it's a fundamental challenge. It forces us to rethink traditional software architecture. We absolutely cannot assume consistent outputs anymore.
So you have to design for that inconsistency.
And you must. Systems have to be built from the ground up with validation, resilience, adaptability as core principles, not just nice-to-haves.
That's a profound point. So if they're inherently probabilistic, how do we control them? How do we get high-quality, relevant, consistent code, especially for critical systems? How do we tame this thing?
Right. How do you steer it? You basically have three primary techniques, each with different trade-offs,
Mhm.
effort, cost, quality.
Okay, what are they?
The lowest effort is advanced prompt engineering. This is all about crafting really precise instructions, context, examples, right in the prompt you feed the AI.
So being a good communicator with the AI.
Exactly. Being specific, maybe giving it a few examples, that's few-shot prompting. Assigning it a role, like you are a senior Python developer.
Right.
Or using chain of thought to make it explain its reasoning.
Okay. And when is prompt engineering best?
It's great for general tasks, rapid prototyping, maybe one-off code generation jobs.
Got it. What's number 2?
Second is retrieval augmented generation, or RAGNA. We touched on this. This technique grounds the LLM's output in external, up-to-date knowledge.
Like your company's code base.
Precisely. You index your private code bases, your API docs, in a vector database. When a query comes in, the system retrieves relevant snippets and adds them to the prompt as context.
Like giving the AI an open book exam based on your specific stuff.
That's a great analogy. It's ideal for generating code that needs to interact with specific, private, or rapidly changing API stuff the model wasn't originally trained on.
Okay, OBRA for custom context. And the third technique.
Finally, we have supervised fine-tuning, SFT, or more efficient methods like parameter-efficient fine-tuning, PEFT. LoRa is a popular one.
This sounds more involved.
It is. It's the highest effort and usually the most costly upfront. You're actually updating the model's internal weights by continuing its training on a curated, domain-specific dataset.
Like training it specifically on your company's coding standards?
Exactly. Code that adheres to your organization's style guides, uses your internal libraries correctly. The payoff is very high accuracy on those specific tasks and consistent style. Plus, you often need shorter prompts to get the desired output afterwards.
So it's like giving the AI a deep specialized education for your specific needs.
That's a perfect way to put it.
Okay, 3 ways to steer the ship. Prompt engineering, RAG, and fine-tuning. So we've got these powerful but non-deterministic models. How do you build a reliable service around that? It feels like you need some serious guardrails.
You absolutely do. To make it production ready, you'd architect a robust code generation microservice.
Bring back the microservice idea.
Yep. This service encapsulates all that logic. It needs an API layer, obviously. A model loader using that factory plus registry pattern we discussed to load models dynamically. A prompt templating engine to manage your prompt engineering consistently.
Right.
Then the core. An inference engine that talks to the LLM and, crucially, handles its non-deterministic nature, maybe with retries or validation logic.
And you mentioned validation.
Critically important, an output validator and sanitizer. You cannot trust the raw output implicitly. You need to check it, clean it, make sure it's safe and correct.
Makes sense. Security and correctness.
Absolutely. Then, a caching layer, especially semantic caching, that understands meaning, not just exact text matches to reduce latency and costs. And finally, comprehensive observability hooks, logging everything for debugging and optimization.
So it's a whole ecosystem just for generating code reliably.
It has to be, to take something probabilistic and make it dependable in production.
That really brings it all together. Okay, now our sources show AI taking this even further, auditing entire workflows just from simple human requests. How do we bridge that gap between, unstructured human intent, I want this to happen, and a structured machine executable plan?
Yeah, how do you turn a wish into code? This is primarily done through structured extraction, using the tool calling or function calling capabilities of modern LLMs.
Of function calling, how does that work?
You provide the model with a schema. Think of a Pydantic base model in Python with clear descriptions of the fields. You tell the model, I need you to fill out this structure, and it generates a strictly conforming JSON object based on the user's request.
So you force it into a structure you understand.
Exactly. And it's more than just pulling out keywords. Take the Jira to Slack notifier example from the sources. The LLM doesn't just see Jira and Slack. It reasons about the data flow. It infers that the output from the Jira trigger the issue details must be the input to the Slack action.
So it understands the connections between the steps.
Yes. That generative reasoning about inputs and outputs is what makes it far superior to older rule-based extraction methods. It's understanding intent and mapping it to a logical workflow structure.
That's a huge step towards AI being a true assistant. So what does this structured extraction mean for building actual runnable workflows, maybe integrating with existing tools?
It leads directly to intelligent node creation in practice. You can plug this into low-code platforms like N8N, for example.
Okay.
The structured extraction system could power an N8N copilot converting natural language descriptions. When a new Jira ticket is created, post its summary to the hashtag dev channel in Slack into the actual executable JSON workflow for N8N.
Wow, generating the workflow directly.
Yeah. Or, for more code-based frameworks like LangGraph, the system can dynamically construct complex state machines or graphs. The LLM defines the nodes, the steps, and wires the connections based on the required inputs and outputs. Highly adaptive.
It's literally translating human thought into a working process graph.
That's the goal.
Okay, here's where it gets really interesting for me. Can AI actually optimize these processes over time, not just execute them, but learn to do them better,
Faster.
cheaper?
Absolutely. And that's where AI-driven process optimization with reinforcement learning, RL, comes in.
Reinforcement learning, how does that apply here?
Okay, think of the core RL concepts. You have an agent that's your workflow orchestrator. It operates in an environment, the system's current state. The agent takes an action.
Like choosing which model to use.
Exactly, like choosing which LLM to route a query to.
Yeah.
And then it receives a reward feedback saying if that action was good or bad.
Okay, so give me an example.
Sure. The sources mention an RL agent learning to route user queries. Should it go to a fast, cheap LLM like, say, GPT-4o Mini, or a slower, more accurate, but more expensive one like Claude 3.5 Sonnet?
And how does it learn?
From user feedback. Maybe a simple thumbs up or thumbs down on the response quality. Over thousands of interactions, the RL agent learns which model works best for which types of queries to optimize a mix of cost, speed, and user satisfaction.
So it's constantly self-tuning based on real results.
That's the power of RL here. Now, it's not easy. RL can be sample inefficient, it needs a lot of data, it can be hard to scale, and designing a good reward function is tricky. But the potential for self-improving workflows is just immense.
Self-improving workflows. Okay, that's a glimpse into the future. Now, our sources also paint this picture of AI not just working alone, but in collaborative teams, like human expert teams. Why are multi-agent systems, MAS, becoming so crucial for complex tasks?
Yeah, the crew concept, the rationale is pretty straightforward. Complex problems are often just too much for one single monolithic superagent.
It gets overloaded.
Exactly. Context overload, loss of focus. MAS mirrors how human expert teams work. You break down the problem, assign subtasks to specialists.
Makes sense. So what defines these multi-agent systems?
A few key characteristics. One is decentralization. Each agent is autonomous. It has its own specialized skills, its own tools perhaps.
Okay.
They operate with local views. No single agent understands the entire problem globally. Each focuses on its specific subtask.
You're right, specialization.
And crucial to making it all work is collaboration. Agents need to interact and coordinate to achieve the overall goal. This might happen through direct communication, shared memory, or maybe a hierarchical structure with delegation.
Okay, let's make this concrete. The sources had a fantastic example. The autonomous DevOps agent crew. How would that work? A team of AIs doing DevOps.
Yeah, the perfect illustration. The high-level goal is something like analyze this code repository, find the most complex function that doesn't have unit tests, generate good PyTest tests for it, check they pass, and then open a pull request.
That's a pretty complex task for an AI.
It is. So you assemble a specialized crew. You have project manager agent, it's the orchestrator. It breaks down that prompt into a plan, delegates tasks to the others.
Okay, the boss agent.
Sort of. Then, a code-based analyst agent. Its expertise is static code analysis. It uses tools to clone the repo, analyze complexity, find that target function.
The specialist for understanding the code.
Right. Then, a test generation agent. This one's an expert in, say, test-driven development. He uses that code generation microservice we discussed earlier to write the PyTest tests, maybe using specific prompts to ensure a certain style.
The code writer for tests.
Yep. Next, a QA engineer agent. This one is meticulous about quality. It takes the generated tests, runs them in a safe, sandboxed environment. If they fail,
it provides feedback.
Exactly. It provides feedback so the test generation agent can iterate and fix the tests.
Ah, a feedback loop.
A crucial one. And finally, a DevOps agent. This agent knows Git, knows CI/CD, it creates the new branch, commits the generated test files, and opens the pull request on GitHub or wherever, maybe even writing the PR description using an LLM.
Wow. That's quite a team, each with its own job, tools, collaborating.
It really mirrors a human software team structure.
So that QA agent feedback loop is interesting. It suggests these systems aren't just linear. If something goes wrong, they can adapt. The project manager doesn't just give up.
Absolutely. That's a key strength.
Yeah.
With the right framework, you can build in these self-correction loops. The QA agent finds an error, tells the test generator, which tries again. It's dynamic, it's iterative.
Not just delegation, but intelligent supervision that adapts. That's a huge leap. So how do you actually build this? What tools let you assemble an AI crew like that?
Frameworks are emerging specifically for this. Crew AI is one mentioned in the sources, used in that DevOps example. It's designed around defining agent roles, their specific goals, the tools they can use, and then orchestrating how they collaborate, often sequentially.
Okay, crew AI for orchestration. Any others?
Well, it's worth mentioning LangGraph again briefly. While Crew AI is great for defining roles and sequential tasks, LangGraph is often better suited for more complex, stateful, and potentially cyclical workflows like those self-correction loops where an agent might need to revisit an earlier step based on feedback. It gives you more fine-grained control over the flow as a graph.
Got it. Different tools for different kinds of agent collaboration? Okay, we've covered a lot. The vision, the architecture, AI writing code, creating workflows, even working in teams. Now let's get real. Where the rubber meets the road, the production challenges.
Ah, yes, day 2 operations.
Exactly. Building a cool demo is one thing. Making these systems reliable, secure, cost-effective in the real world, that's a whole different ballgame.
It absolutely is.
Yeah.
And the challenges are significant. Let's start with security threats. Agentic AI systems introduce some really novel dangers. The big one is prompt injection.
Prompt injection.
Yeah, LLMs fundamentally struggle to distinguish trusted system instructions from untrusted user input.
So a user could trick it.
Easily. With direct prompt injection, a malicious user just tells the agent, ignore all previous instructions, do this harmful thing instead. Or maybe, tell me your system prompt.
Okay, that's bad.
It gets worse. Indirect prompt injection is more insidious. An attacker might poison an external data source, say, hide malicious instructions on a web page or in an email that the agent later reads.
And the agent just executes the hidden command?
Potentially, yes. Turning it into a spam bot or making it exfiltrate data. There's also prompt leaking, tricking the agent into revealing sensitive internal info. And insecure tool use, manipulating the agent into using powerful tools like shell access or database, writes maliciously.
These sound like serious new kinds of vulnerabilities.
They are. We need new defenses.
So what are the mitigation strategies? How do you build an AI firewall?
It has to be multi-layered. First, strict privilege control. The principle of least privilege is paramount. Only give agents access to the absolute minimum tools and data they need for their job.
Don't give the test-writing agent database write access.
Exactly. Second, human in the loop. For any high-risk action deleting data, spending money, contacting external systems, you need mandatory human review and approval. Period.
A human safety switch.
Essential. Then, input-output sanitization and validation. Use specialized moderator LLMs to pre-screen user inputs for malicious intent. And crucially, force structured output wherever possible, like using pedantic schemas. This prevents malformed commands or code injection through the output.
Structure as a defense.
Yes. Also, segregation of external content. When an agent reads from an untrusted source like a web page, wrap that content in clear delimiters, like XML tags, and explicitly instruct the agent not to execute any instructions found within those delimiters.
Telling it, this part is just data, don't trust instructions here.
Precisely. And finally, parameterized tool inputs. When an agent calls a tool, like running a shell command, don't just pass raw strings from the LLM. Use parameterized inputs to prevent command injection vulnerabilities.
Okay, a comprehensive defense strategy. But security isn't the only headache. What about cost? These LLM API calls, priced per token, that can escalate fast, right? Especially with multiple agents making calls.
Oh, absolutely. Cost can spiral out of control if you're not careful. Cost management strategies have to be baked in from day one.
So what can you do?
First, granular monitoring. You cannot optimize what you don't measure. Tools like Helicone, Langsmith, and others are vital for tracking costs per user, per agent, per task, even per specific prompt template. You need that visibility.
To know where the money's going.
Exactly. Second, intelligent caching. We mentioned response caching, but semantic caching is even better. It caches responses based on the meaning of the prompt, not just the exact text. Saves a lot on similar queries.
Smart.
Third, model routing and cascading. We touched on this with the AI gateway. Send simple queries to cheap models, complex ones to expensive models. It's about using the right tool for the job, economically.
Optimize the model choice.
Right. Fourth, prompt optimization. Regularly review and refine your prompts. Can you get the same quality output with fewer tokens, fewer examples? This is a high-leverage activity.
Tuning the prompts themselves.
Constantly. And fifth, strategic fine-tuning. For high-volume, repetitive tasks, fine-tuning a smaller, maybe open-source model might be expensive up front, but it can lead to significant long-term savings if that model becomes much more efficient for your specific use case.
Investing in efficiency for the long run.
Exactly. It's a trade-off.
Okay, so cost management is about visibility, caching, routing, optimization, and strategic investment. And finally, the third big production challenge. How do you make sure these things keep working well? How do you handle model drift or unpredictable emergent behaviors? It works today, but what about next month?
Yeah, the ongoing monitoring and maintenance. The day two reality. We had several things here. Comprehensive logging and tracing is non-negotiable. Log the entire execution, trace inputs, outputs, intermediate thoughts of the agent, tool calls. Tools like Langsmith are indispensable for this deep visibility.
Seeing exactly what happened.
You have to. Then, explicit user feedback mechanisms.
Yeah.
Simple thumbs up, down buttons, feedback forms. Getting high-quality human feedback is invaluable for identifying problems and improving the system.
Closing the loop with the user.
Essential. Also, automated evaluation and regression testing. You need a golden data set, a set of representative prompts with known good outputs. Run these automatically in your CI/CD pipeline to catch performance regressions before they hit production.
Automated QA for the AI.
Pretty much.
Mm.
And finally, anomaly detection and monitoring on key metrics. Track latency, cost per transaction, error rates, maybe semantic drift scores. Set alerts for significant deviations. This helps you spot problems like model drift or unexpected behavior early. Recognizing, of course, the observability trilemma, always balancing completeness, timeliness, and the overhead of the monitoring itself.
Wow. Okay, that's a lot to consider for production. Security costs, ongoing monitoring and maintenance. It's definitely not just plug and play.
Not at all. It requires serious engineering discipline.
What a journey we've taken today, though. From understanding the fundamental architectural shifts
Microservices, MAAS, the AI gateway.
to the design patterns, how AI actually writes code, how it builds workflows,
Prompting, RA, fine-tuning, structured extraction.
all the way to building collaborative AI crews and tackling those really tough production challenges.
Security, cost, observability.
Yeah, it's crystal clear that the role of the software developer is profoundly evolving, isn't it?
It absolutely is. And I think the core takeaway from all these sources is this. The most valuable engineering skills are shifting. They're moving away from just manually churning out code
Towards what?
towards systems thinking,
Right.
robust architectural design, and the ability to precisely define, orchestrate, and critically govern the behavior of these intelligent autonomous agents.
So it's about building with AI, not being replaced by it.
Exactly.
Yeah.
The future doesn't belong to those who are replaced by AI, but to those who learn how to build with it, how to leverage it effectively and responsibly.
That's a powerful thought to carry forward. And maybe a final thought for you, our listener. As you think about how these agentic systems could transform your own work, your organization, consider this. What existing, complex, maybe tedious, human-driven process in your world?
Something that takes a lot of coordination or manual effort.
Right? What process, if you reimagined it through the lens of a collaborative AI crew like the ones we discussed, what could achieve truly unimaginable scale or speed or efficiency?
It's a fascinating question to ponder.
It really is. Thank you so much for joining us on this deep dive today. We hope you'll explore more, dig into some of these concepts, and maybe start thinking about how you can apply this knowledge.